Okay, how's the volume? How's the
It's good.
volume? It's fine. Okay, so this is joint work with Amir Amir, Ayelet Butman, Gadi Landau, and Shoshana Marcus. Now, mostly everybody knows what a tandem repeat is, but you probably never heard of a double string. So I'm going to define a double string and a double string tandem repeat. And once we're done with the definition, we're going to present an outline of an algorithm to find these double string tandem repeats. Now, the reason we were interested in this problem is that there are two problems that we were working on simultaneously, variations of tandem repeats that are unrelated to each other, and we realized that both of them reduce to the problem of double string tandem repeats. And so we first talk about the problem of double string tandem repeats and then show you those applications. The first one is called corner sharing tandems on a two-dimensional text. And the second problem is scaled tandem repeats. This is in a one-dimensional string searching for scale tandem repeats. So again, a tandem repeat, we all know, is a string that occurs contiguously 2 times. Has to be one right near the other and has to be identical for this work. So here we have ABC, and right following it we have again ABC. What's a double string? A double string is simply 2 parallel strings of the same length. So you might be thinking, oh, like a double helix. But it's not exactly a double helix, because a double helix is a relationship between the symbols. So the 2 strings are, you only need to deal with one string. You don't even need to use both strings. Here we relax that requirement. We have 2 strings of the same length. We index them together, but there's no relationship between the symbols in S1 and in S2. So it's a double string tandem repeat. Now that we have a different kind of input, we define a tandem repeat as 2 copies of the same pattern, where one of the patterns occur in S1 and the second copy occurs contiguously in S2. So they have to meet exactly. So here we have ABC, and starting at location 5 in S2, we have ABC again. That's a double string tandem repeat. One of the copies we call the root of the tandem or the period of the tandem, just like we would do in one string. So when you start thinking about it, you realize that you could have lots and lots of tandem repeats. For example, if you have all A's and all A's, you have period 1, and then you have period 2, period 3, etc., etc. And when we look at tandem repeats in one string, what we do for them is we represent them as a run or as maximal runs. And the question becomes, can we take these double string tandem repeats and represent them also in a compact way? So just to review quickly what a maximal run is, if you have a string of A, B, A, B, A, B, you would say, well, we have lots of tandem repeats. They're all contiguous, and the period is 2. You could also start at location 2 and have B, A, B, A. But you might say, I also have period 4, I also have period 6. And what we say is, but those aren't interesting because they're all represented in period 2. They're just multiples of 2. And if you know that you have 2 and you know the length, then you know that you have 4 and 6 as well. So what we do in this situation is we encode this run as a triple, and we just have one output for this kind of string. And we say there's a tandem, there is a run starting, the leftmost tandem repeat starts at location 1, the rightmost tandem repeat starts at location 10, and the period size is 2. And that encodes everything about all tandem repeats that we have in this sequence. So we move to 2 strings. Well, we call a double string sometimes a 2 string. We move to the double string and we say, can we define a run? Kind of similar by saying it's a sequence of consecutive tandem repeats. And then we'll say it's maximal if it can't be extended to the right or the left. So let's see what happens when we do that. Here we have a double string, and right starting at the beginning, there's a double string tandem repeat. But if we move over by 1 character, you see we also have a double string tandem repeat, all with the same period, size 3. So of course, just like any run has to have one single period size, a run in two strings also has one period size. And as we move along, we see that the first three periods were conjugates of each other, like we have in runs in one string. But then the period starts changing, but it's still size 3. So what we say is, okay, we could still talk about a run here, because we could still say, like we have this encoding 163, the leftmost tandem repeat starts at 1, the rightmost tandem repeat starts at 6, and the period size is 3. So we're happy because we still have an encoding. But then we ask ourselves a question. Okay, this is the maximality. Same concept, extends to the right, extends to the left, and is a maximal run. And we say, great, we could encode double string tandem repeats as a maximal run, what we call a 2-string run. Takes care of everybody. But then we ask ourselves this question about primitivity, because with one string, we only report period size 2, as I showed you before, and we don't say 4, we don't say 6. Does this also apply in runs in a double string? And the answer is it's not so simple. Let's take, for example, this double string tandem repeat that has a period of ABAB. ABAB is clearly not sorry, I didn't define primitive, so let me just define primitive here. Something is primitive if it cannot be written as a string with an integer exponent. So ABAB is what we call non-primitive, because it can be written as AB squared. And the root here is non-primitive. So you might say, no, just talk about a root of size 2. Don't talk about period 4. But if you look at the root of size 2, it doesn't tell you anything about the fact that 1 and 2 match 5 and 6 in the other string. So you definitely will be missing a lot of information if you say only report the primitives. And furthermore, you can take a look at a run in a double string, and you'll see that you could have some repeats with primitive periods and some repeats with non-primitive periods, all in the same exact run. So here we have XBAB, that's a primitive root. You wouldn't want to break that down, and you would want to report it. But right next door to it, you have BABA, which is again non-primitive. And as you go on, you'll see you'll have some with and some without. So it becomes very unclear of what you want to do with primitivity in these double strings. It sort of looks like you better report everything, because you're going to be missing a lot if you stick with only the smallest size. And so we decide that we are going to ignore primitivity and report everything. I'm just going to comment that it really is possible to post-process your output, because the things that are non-interesting, like with what we had with all the A's, you could find in each one of the strings the runs of all A's, and you could realize that those things will be non-interesting with a double string. Okay, so just to sum up the discussion about the definitions, what we're searching for are all maximal 2-string runs. So those are maximal runs inside of double strings, which are one or more 2-string TRs or double string TRs with the same period size occurring consecutively. And periods may be primitive or non-primitive. So in this example, the maximal run would be 144, saying the leftmost tandem repeat starts at 1, the rightmost tandem repeat starts at 4, and the period size is 4. And it means that everybody in between is a tandem repeat of size 4. Okay, so then we want to find these things in a given double string. And what's interesting is that the Main-Lawrence algorithm extends really nicely to this problem. Now let's remind you what the Main-Lawrence algorithm does. Instead of searching every start point or every substring or anything for a tandem repeat, we rather search for tandem repeats that cross a given point. I'll have a figure on that in a moment. And once you find those tandem repeats that cross that given point, you split your input into two halves and you find those that cross the midpoint of the first half and those that cross the midpoint of the second half. So here it is in figure form. You find everybody, if you're looking at your top level of your string of length n, you find everybody that crosses the midpoint, and then you process the left and the right, finding everybody that crosses the midpoint iteratively or recursively, no more than log n iterations. Now, how do we find everybody that crosses the middle point? And what Main and Lawrence do is they compute the longest common extension, moving forward and moving backwards. Since all you really need to know, since you're fixing your period, is all you really need to know is that does the character that's P away from you for period P match? And again, I'll show this in a figure in a moment. What's interesting here is that the forward comparisons and the reverse comparisons can be done just exactly the same way, just using the two strings. And here we have it in the picture. So again, we fix our period P, and we do this for every possible period. We're looking for things that cross the midpoint. So we start inside out from the midpoint. We compare n over 2 to n over 2 plus p moving forward, and we see how long can we match. And let's call that delta 1. Then we go ahead and look in the reverse, and we say how long do we match backwards, and we call that delta 2. And notice this is very different than the Main and Lawrence because we have two input strings here. So the first forward extension is in S1, the second forward extension is in S2. It's the same thing for the reverse extensions, and yet we can still say that you found yourself a run if your length is greater than or equal to P. And your run is going to extend all the way from the left, or wherever you matched, until all the way until the right. I'm going to give you a little example of a simulation. Thanks to Lorenzo for this one. And it's a very, very simple example because we're going to look at period size 1, which, you know, period size 1 in one string would have to be all A's or all B's or all any character. But a double string tandem repeat with period size 1 just means that each tandem repeat in the run matches its consecutive character in the other string. So we begin by looking at everything that crosses the midpoint. Since P is equal to 1, our period size is 1, our second string for the extension starts at mid plus 1. We match forward as much as we can, and all we can match is the single C. We match a reverse extension as much as we can, and we go all the way back to location 5. And then we simply say, okay, since delta 1 is greater than, delta 1 plus delta 2 is greater than P, we have a run from all the way extending from 5 to 9 with period size 1. For a second, you see this, you say, where is there a run here? But let me remind you, this is double string tandem. So as long as the X matches the X, we have a double string tandem of period 1, and the Z matches the Z, and so on. So that is how this algorithm plays out with the two strings. Now I'm going to skip the pseudocode and everything and just tell you that it also has the same runtime as Main and Lawrence, the n log n. And you can see the paper for all the details, but I prefer to get to those applications rather than the details of the algorithm. So application 1 is a problem defined by Apostolico and Brimkov. It's a problem on a two-dimensional text. And it says we want to find tandem repeats in a two-dimensional text. But where should these two copies meet? And the answer is, in this definition, these two copies meet at a corner. So you have two copies of the same two-dimensional text, and they meet at a corner. And they're called corner sharing tandems. And they could go in the other direction as well, but that would actually correspond in the double string to having your first copy in S2. Okay, we'll get there. So Apostolico and Brimkov actually define this. They give an n to the 4th time algorithm. And by using the double string tandem repeats, we can reduce the time to n cubed log n. So the first step in this reduction would be to see whether we can define a run of these corner sharing tandems. Now, it's not intuitive right away to say a run. These things are attached at a corner. What do you mean by a run of corner shearing tandems? Well, what do we mean by run? A run means contiguous tandems. So if you have a corner shearing tandem with period 3 by 4, and then right next door, another corner shearing tandem, and also with the same exact period, 3 by 4, you could connect them and say this is a run of corner shearing tandems. And so we do define a run of corner shearing tandems. The paper will prove how many you can have of those kind of runs in a two-dimensional text. And then we show that this problem is actually an instance of the double string tandem repeats problem. How do we go about that? What we do is we actually do naming on subcolumns of the text. And you need to do this for every possible height, and you need to do it in every row, and I'm going to just show you 2 rows specifically for height 3. So we take these subcolumns of height 3, and we name them such that every 2 subcolumns of height 3 that are identical get identical names. Again, we're going to be doing this for every single row for height 3, but I'm only showing you the first row, and then I'm going to be showing you the 4th row, because those are the rows that we look at for this particular example. So we got ourselves 2 rows of names of height 3, and that can be done by constructing a suffix tree of the columns of your text. And while you're constructing the suffix tree, you put down those names according to the nodes that you hit. And we went ahead and converted our problem from 2D into a double string problem. How is it a double string problem? Well, since these are exactly 3 away from each other, these 2 rows, a corner shearing tandem turns into a double string tandem repeat in these 2 strings. And in fact, a corner shearing run turns into a double string run in these 2 strings. Okay, so I'm not going to, again, I won't do the details of the pseudocode, but the idea is I just want to point out that when you're looking for height H, you look at row R and row R plus H in the text that has names of height H. And that gives you the n cubed log n time that we promised. Okay, so the last couple of minutes we'll put into the scale tandem repeats problem. The scale tandem repeats, in order to define them, I'm just going to first remind you about run length, where you replace NAs with a to the n. And here's an example of a string replaced with its run length of the string. An e-scaling of a string S means that you replace every character in the string S with e copies of the same character of the string. So in this example, we're using the run length to represent S. Instead of having 3 A's, you put in 5 A's. Instead of 2 B's, 5 B's, etc. So what's a scale tandem repeat? A scale tandem repeat is a string U prime, where U prime is an e-scaling of U for some integer E. Here's an example. The first copy has 2 A's, so the second copy, we're using E is equal to 2, so we're using an a 2 scaling. The second copy should have 4 A's, and there you have 4 A's in the second copy. The 1B turns into 2 B's, the 1C turns into 2 C's, and the 2 B's at the end turn into 4 B's, with the border of the 2 copies right where the arrow is. Obviously, the sizes of these 2 copies is different because one of them is a scaling of the other one, but it's a very interesting problem, and we looked at it for a while before realizing that we can actually transform this as well into a double string problem. Now that we're running out of time, I'm going to skip all of those slides, and I'm going to point out first that you can define actually a scaled run. So it's really not intuitive because your 2 copies of your runs have different lengths. So what do you mean by a scaled run? But the answer is that as you move over, if you're looking at the same scale, you could keep, as long as you can keep moving over with the same scale, you may have consecutive scaled tandem repeats with the same scale, and you could therefore link them up and call them a run, and you could go ahead and search for scaled runs. Now, the first thing we do in order to do that is we split our text into the characters and the exponents. And in order to find a scale tandem, we have to find it as a regular tandem in the character text, and then also as a tandem in the exponent text. But the difference is that you have to look for it as a tandem in the exponent text with a scale. So you go ahead and you search them both separately. It's obvious for the characters, you just do a regular tandem repeat search. And for the scale matching, we use a compact regions data structure, which means that you go ahead and create a whole bunch of texts, one for each possible exponent in your text, by dividing the exponents. So for example, just look at T2. T2 means that you divide every exponent by 2, and you create yourself a text. Now, there's some details that you have to add dollar signs, which there's no time for, but you create a T for each one of the exponents, and you get what's called a compact regions data structure. It can be constructed a linear time. Its size is linear in your original string. And then what you have is a scaled tandem repeat actually turns into a double string tandem repeat between your original text and one of your texts in your compact regions data structure. Because whatever your scale E is, take a look at T sub E, and you're going to find that the second copy is identical to its first copy. And there you have it. And it works for the runs as well. So you have a scaled run, and it turns in exactly into the same string. So you have to do it for each E, for each possible E, but then you're going to find it as, you'll find all of your scaled runs, all your scaled tandems as a double string tandem repeat. Any questions?
So thank you for the talk, Dina. We have time for a short question.